Hello everyone. So today we are going to talk about expectations. Expectation, in a simple word, you can say just average. But we are familiar with the word average when it comes to just measuring deterministic values. But in this chapter related to probability, what does average or expectation means? The expected value or mean of a random variable is defined as the sum of the random variable multiplied with its probability. So random variable, as we learned last week, is a function that assigns values to its sample space elements. So given a sample space S, it takes value an element from that sample space little s and it assigns the value, and expectation is the product of that value with its probability and sum on all over that sample space. That's it. Using that particular formula, we will solve these problems related to expectation. So let's try an example, a simple one, to understand what expectation means. So example 18. Suppose we toss a fair coin 3 times. Let xh denote the number of heads that appear. What is the expectation of xh? That means, what is the average number of heads appear when we toss a fair coin 3 times? So first we are going to use the definition and solve it using that. Let's call that method 1, and later on using other methods we will solve this same problem to get a better understanding of the problem itself. So since expectation is value times probability for all the elements in the sample space, what are these different elements in the sample space? So what happens when you toss a fair coin 3 times? What are the different outcomes? So let's say we write the outcomes first. If we toss a fair coin 3 times, the outcomes can be head, 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 tail, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, tail, and 3 tails. Okay. Now, what is the value for the random variable xh for each of these outcomes? So for each of these outcomes, we are going to count how many heads are there and we are going to write it. So 3 heads, so the value of the random variable is 3. 2 heads, so it's 2, 2, 2. 1 head, so 1, 1, 1, and 0 heads, so it's 0. Next, we calculate the probability for each of these outcomes. So what is the probability that you get 3 heads if you toss a fair coin 3 times? So the first one being head is half, second one is half, third one is half. So the total probability that this will be your outcome is half times half times half, which is 1/8. So we just know that it is 1/8 for each of these outcomes since it's a fair coin. This is not always true. It depends on the problem, and from all the theorems and all the examples that we have studied in this chapter, you should be able to calculate, given an outcome like this in an experiment like this, what is the probability. So for this, each of these probabilities are just 1/8. Now what is the formula for expectation? We know that this is value, this is probability. So we are going to do value times probability and we will add all of them. Okay. So the expectation of this variable is 3 times 1/8 plus 2 times 1/8 plus 2 times 1/8 plus 2 times 1/8 plus 1 times 1/8 plus 1 times 1/8 plus 1 times 1/8 plus 0 times 1/8, which is equal to, if you take the 1/8 common out, 3 plus 2 plus 2 plus 2 plus 1 plus 1 plus 1 plus 0, which solves to 12/8, which is 3/2 or 1.5. So this is the value for the expectation. So to recap this problem's solution, we find out each outcome, we find out the value of the random variable for each of these outcome, we find out the probability of each of these outcome, and then we do value times probability and we sum all over this sample space. Whatever the value is, that is your answer. So what does that mean? In one simple sentence, that if you toss a fair coin 3 times, the average number of heads you are going to get is 3/2 or 1.5. Now it is not a coincidence that that would be your intuitive result. If you toss a fair coin 3 times and every time the probability of getting a head is half, then half of the times you will get a head. So total number of heads on an average, or the expected number of heads, is 3/2, 1.5. Now we'll try to solve it using a different method, a second method. For that, let's look into the next lemma. Let x be a random variable, then the expectation of x is equal to summation of all the possible values for the random variable, and you do that value times the probability. It's writing the same formula in a different way, because sometimes writing it in this way will be more helpful and easy. So let's do that. So what are the possible values for this random variable xh? That means if you toss a fair coin 3 times, what are the different values or different number of heads can you get? We can get 0 heads, we can get 1 head, 2 heads, or 3 heads. That's it. Nothing more or less. So xh belongs to the set 0, 1, 2, 3. The values can be 0 or 1 or 2 or 3. So using this formula, let's do this. The expectation of the variable xh is equal to 0 times probability that xh is equal to 0 plus 1 times the probability that xh equal to 1 plus 2 times the probability that xh equal to 2 plus 3 times the probability that xh equal to 3. Okay, and then for each of these values we know them, and we'll just calculate the probabilities. using our knowledge from previous chapters, and we'll plug in those values and we will get your answer. So 0 times probability that XH equal to head. So using the knowledge from combinatorics, you know that the denominator is 2 to the power 3. There are 3 coin tosses, so number of outcomes is 2 to the power 3 or 8. And in how many cases there are 0 heads? That is exactly 1 case. Plus 1 times, what is the probability that if you toss a fair coin 3 times, you will get exactly 1 head? So if you are tossing a coin 3 times, there are 3 tosses or 3 spots, and one of them is head. So 3, choose 1. 2 times, what is the probability that you will get exactly 2 heads? So there are 3 tosses and you are choosing 2 of them to be head, so 3, choose 2. Similarly, 3 times, this is 3, choose 3 over 2 to the power 3. Now instead of 1, you can also express it as 3 times 0. That's how we got 1. So if the probabilities are clear that for number of heads is 0, 1, 2 or 3, see 3 comma that value, because that's the probability that you are getting how many heads are there over 2 to the power 3. Now let's solve this. 0 times, this is 1 over 2 to the power 3, plus 1 times, this is 3 over 2 to the power 3, plus 2 times, this is 3 over 2 to the power 3, plus 3 times, this is again 1 over 2 to the power 3. So 2 to the power 3 is the denominator, the numerator is 0, plus 1 times 3 is equal to 3, plus 2 times 3 equal to 6, plus 3 times 1 equal to 3. The numerator adds up to 12, the denominator is 8, which is 3 over 2 equal to 1.5. So we learned 2 different methods, and both methods give us the same result, 1.5. Now we will continue with same example 18, and we will learn a third method, but for that we have to learn theorem 5, linearity of expectations. If you look into the handout, the first theorem is let xi for I equal to 1 to n, that means x1, x2, x3 up to xn, be all random variables on the same sample space S. Then expectation of x1 plus x2 plus up to xn is equal to expectation of xn, x1 plus expectation of x2 plus expectation of xn. And the second part is, if let x be a random variable on S and a and b are 2 real numbers, then expectation of a times x plus b is a times expectation of x plus b. How will that help us solve this problem? Let's see. This time we rephrase this problem differently. Let's say we are still counting the expected value of xh. Let xi equal to 1 if the coin turned up heads, and it is equal to 0 otherwise. So x1, x2 and x3 represent the random variable associated with the outcome of the first, the second and the third coin respectively. So we will just calculate the expectation of x1, and we will figure out what is its relation with expectation of x2 and x3, and then using the formula or the theorem about linearity of expectation and our knowledge that xh is equal to x1 plus x2 plus x3, we will solve the problem. So let's see. So x1 is a random variable associated with the first coin. So let's say it is 1 if the first coin or the first toss is head, and equal to 0 if the first toss is a tail. Okay, so that's our random variable x1. So x1 is 1 if it is a head, x1 is 0 if it's a tail. So what is the expectation of this particular random variable x1? We will use the formula we have already learned. It is 1 times the probability that x1 equal to 1 plus 0 times the probability that x1 equal to 0. Those are only two values x1 can have. Let's see. 1 times, what is the probability that x1 equal to 1? Means, what is the probability that the first toss is a head? So this is a fair coin, we tossed it, and what is the probability that the first toss is head? It's half, because it's fair coin. And 0 times, what is the probability that x1 equal to 0? That means what is the probability that the first toss is a tail? Again, half. So 1 times half plus 0 times half is equal to half. So expectation of x1 is equal to half. Now we do not have any reason to believe that it is different for other coin tosses. It's the same. The first toss, the second toss, the third toss, they are all the same. So their expected values are same. They are all half. And what is the value of expectation of xh? Now expectation of xh means xh can be written as x1 plus x2 plus x3. You know that from the problem statement itself, and also the fact that each of these variables count whether that particular toss is a head or tail, and if you add them all up, then the final answer is xh, the number of heads. So E of xh is equal to E of x1 plus E of x1 plus x2 plus x3. And now using the linearity of expectation, the theorem that we just learned, we can write that it is E of x1 plus E of x2 plus E of x3. So this is the application of the linearity of expectation. And for each of these, we know the answer. They are all half. So half plus half plus half, which is 3/2 or 1.5. So this is the third method we learned, and we solved this problem using linearity of expectation, and we got the same result, 1.5. Now let's go back and solve another problem, example 19, to understand how to use random variables to get the expected value of that random variable. Example 19 is, in a pick 6 lottery, there are 6 numbers and you choose them from 1, 2, 3, 4 up to 40, these 40 numbers or these 40 integers. So there are 40 integers and you choose 6 from that set without replacement. So it's like there is a bucket and there are 40 balls with numbers labeled on them 1, 2, 3, 4 up to 40, and you choose 6 of them together. So the winning ticket is $1 million and every other ticket is 0. So there is only one winning ticket, and if you win it you get $1 million and everything else is 0. You bought one ticket. What we are trying to calculate here is the expected winning. What is the average winning? That is, let X denote the winning amount from a single ticket, and we are going to calculate the expected value of it. So let's write down the value of X as a random variable. So X is equal to $1 million if you win, and is equal to 0 if you lose. So that's the value of this random variable. It's either $1 million or 0. We are trying to calculate the expected value of X. So now we know the formula. It's the value 1 million times probability of winning plus 0 times the probability of losing. Okay, so 1 million times what is the probability of winning? That's the one thing that we have to calculate. So there are how many tickets? You have total 40 numbers and you are choosing 6 from them. So there are total 40, choose 6 different tickets. And as we know, for this problem there is exactly one winning ticket. So the probability of winning is 1 over 40 choose 6 plus 0 times something. We don't even have to calculate the probability of losing. It's 0. Now, so it's 1 million over 40 choose 6 plus 0 equal to, so if you divide 1 million by 40 choose 6, you get an approximate result is $0.26. So your expected winning is approximately $0.26 or only 26 cents. And that gives us a perspective about lotteries. So in this game where there are 40 choose 6 total tickets and there is only one winning ticket, the winning ticket is $1 million, all the other tickets are 0. In that case, the average winning or the expected winning is approximately 26 cents. Let's do another problem related to expectation. Our next problem is example 20, the hat check problem. Suppose n men checks in their hats in a restaurant. Now unfortunately all their hats got mixed up. So when all of them came out and tried to pick their hat, they randomly picked one hat and got home. Now our problem is, on an average, how many will get their own hat back? So mathematically speaking, what is the expected value or expected number of people who got their own hat back? Now the problem is trying to find out what is the expected number of men that got their own hat back. And for this type of problems, for whichever value that you are trying to calculate or trying to do the expectation on, you have to choose that as your random variable. Then you just calculate the expectation of that random variable and it would be easy to solve the problem. So we define x as that random variable. X is the number of men who got their own hat, and we are trying to calculate the expectation of x. So if x is the number of men who got their own hat back, what is E of x? So for that, let's use another random variable, xi. What is xi? Xi equal to 1 if the ith man got his own hat back, and equal to 0 otherwise. So xi, just like the coin problem, we will focus on individual men. Xi equal to 1 if the ith man got his own hat back, and it is 0 otherwise. So in this case also, x equal to summation of all the xi's, or in other words, it's x1 plus x2 plus. We know all these probabilities, so 1 times probability of xi equal to 1 is 1 over n, plus 0 times whatever it is 0, equal to 1 over n. So the probability of, or the expectation of xi, E of xi equal to 1 over n. Now how do we calculate E of x that we have to calculate? Expectation of x equal to, we know that x is equal to summation of all xi, so we can write this, E of x equal to E of x1 plus E of x plus x2 plus dot 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 up to xn, because x is equal to x1 plus x2 plus up to xn. And then we can use the linearity of expectation. So E of x1 plus x2 plus up to xn is equal to E of x1 plus E of x2 plus dot 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 E of xn. And for each of these xi, they are same. There is no reason to for them to be different. So E of x1 is equal to E of x2. They are all 1 over n. So E of x1 is 1 over n plus 1 over n plus dot 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 to 1 over n, which is, there are n terms, so it is n times 1 over n, which is equal to 1, and that is our final result. E of x, or the expected number of men who will get their own hat back, that results to 1, just exactly 1. Now this is an interesting result. The final result 1 does not depend on the value of n. So it doesn't matter what is the value of n. It does not matter how many men are there in that restaurant. If they are picking randomly their hats, the expected value, or on an average exactly one person will get their hat back. Next, let's do the last problem, problem 21, inversions in a random sequence. So in a sequence of n numbers, a1, a2, a3 up to an, a pair ai and aj form an inversion if I is less than j but ai is greater than aj. Now for all these numbers we are assuming that they are distinct or they are different, there is no repetition. So if we arrange these numbers or this sequence randomly, what is the expected number of inversions in this sequence? So to understand this, let's do some examples. Let's say this is our sequence 1, 2, 4, 5, 3. So there are 5 numbers and we arranged them in this order 1, 2, 4, 5, 3. And how many inversions are there? So in inversion would be if a smaller number is on the right side of a bigger number. So this is an inversion and this is an inversion. So the two inversions are 3, 4 and 3, 5. So in this particular sequence 1, 2, 4, 5, 3, there are 2 inversions. Okay, so hopefully this is now clear what an inversion is. We are trying to calculate the expected number of inversions. So again, it would be good to have that random variable. So x is the number of inversions so let's say we assign x as the random variable, that is the total number of inversions, and we will have to calculate the expected value of x. So what is e of x? Again, we will break it down to a smaller random variable. So let's say xij. This is a random variable and this is equal to 1 if the pair ai and aj form an inversion, and is equal to 0 otherwise. So in this case, in this example, the pair 3, 4 forms an inversion because 3 is on the right side of 4. The pair 3, 5 forms an inversion because 3 is on the right side of 5. But the pair 1, 2, they do not form an inversion because 1 is on the left side of 2. The pair 2, 4 does not form an inversion because 2 is on the left side of 4. So for this pair, the random variable xij will be 0. For this pair 2, 4, the random variable will be 0. But for this pair 3, 4, the random variable will be 1. For this pair 3, 5, the random variable will be 1. For this pair 4, 5, the random variable will be 0. Hopefully this helps you understanding what an inversion is. So now that we have done xij, we have defined xij, this random variable, we want to find out what is the probability of xij being 1. So what is the probability that xij equal to 1? That means what is the probability that this pair ai and aj form an inversion? Okay, now this is simple. Why? This is just half. Why is that? since given a pair AI and AJ, that I is less than J and I is greater than J, they are equally likely. Since all these arrangements or all these permutations are random, half the time AI and AJ will form an inversion. That means half of the time given any pair AI and AJ, I is less than J, and half of these permutations I is greater than J. So the probability that the pairs AI and AJ form an inversion is half. Okay. Now, what is the expected value of this particular random variable then? What are the possible values of Xij? This is 1 and 0. So we do 1 times probability that Xij equal to 1 plus 0 times probability that Xij equal to 0. 1 times Xij equal to 1, we just calculated its half, plus 0 times, it will be half, but 0 times anything is 0, so it is half. So E of Xij is half. Now, how do we write X with respect to Xij's? So with n numbers, there are n choose 2 different pairs and we sum them all over Xij. So X is summation of all Xij's, and expectation of X is equal to expectation of the summation of all Xij's. For both case, I is less than J. Okay, and using the linearity of expectation that we know, we can take the sum outside. I is less than J, this expectation of Xij. That is summation of this value. Now this value we know that is half. Now how many pairs are there? We know that is n choose 2, and for each pair the value is half, so n choose 2 times half, which is n times n minus 1 over 2 times half. So the final answer is n times n minus 1 over 4. That is your final answer. So the expected number of inversions is n times n minus 1 over